Okay, so welcome to this next video in which we are discussing the phospholipase C gamma enzymes. Okay, right, so we now want to discuss how both phospholipase C gamma 1 and phospholipase C gamma 2 are going to be activated by phosphotyrosine residues on the intracellular aspect of receptor tyrosine kinases. So, firstly, what's going to happen is the inactive phospholipase C gamma enzyme, which is currently within the cytoplasm, is going to bind to the phosphotyrosine residues of the receptor tyrosine kinase, okay? And this is going to recruit it to the underside of the phospholipid bilayer. Now, how is it going to bind? Well, it's going to bind using this N-Sarc homology 2 domain, so this one here. Okay, so the N-SH2 domain is going to bind to a phosphotyrosine residue within the intracellular aspect of the receptor tyrosine kinase. Okay, so let's draw this now. Okay, now this isn't going to activate our phospholipase C gamma enzyme yet. It's just going to recruit it at the phospholipid bilayer. Okay, so now I will go over to drawing the phospholipid bilayer as two layers, okay? So two layers of phospholipids, the inner leaflet and the outer leaflet. Okay, so here once again are my two receptor tyrosine kinases, which we are presuming is epidermal growth factor receptor. Okay, so here are my two epidermal growth factor receptors bound together, and they both therefore have an epidermal growth factor molecule bound to them. Okay, so once again I'll colour in the epidermal growth factor molecules in blue here. Okay, and then I'll colour in the epidermal growth factor receptors in red. Okay, and they've changed conformation so that they can now dimerize together in this way. Okay, right. Now let's draw their cytoplasmic domains, and let's assume that they have undergone autophosphorylation, where the tyrosine kinases the tyrosine kinases have phosphorylated the tyrosine residues on the opposite epidermal growth factor receptor. Okay, so here's our tyrosine kinase domain here, and here is our tyrosine kinase domain on this opposite one. And now we'll just draw one of these tyrosines because we're only going to need one. Okay, and it will be too difficult to draw multiple of them. Okay, it will get too squashed. So the single letter code for tyrosine is Y. So that's why I put a Y there, just to denote tyrosine. Okay, and it now has a phosphate group attached to it. And what's now going to happen is this SH2 domain within the XY linker is going to come and bind to this phosphotyrosine residue, and that's going to recruit the phospholipase C gamma enzyme at the underside of the phospholipid bilayer. Okay, so let's draw this then happening. So I'll try and draw the picture once again. Now, how am I going to do this? It's difficult because I want the SH2 domain, the NSH2 domain, to be bound to that, but I'll just have to try my best. So let's put in our XY barrel here, okay, and at the moment the CSH2 domain is still going to be in there, and it's still going to be blocking the catalytic core of our phospholipase C gamma enzyme. Okay, right, so here are the two halves of our tin-like barrel domain, the X and the Y box here. Okay, now after the X box, we have that first half of the split plextrin homology domain, which will then be bound to the other half that comes over here. Right, now I want to show this NSH2 domain bound to that phosphotyrosine residue, so that's what I'll have to show there. Okay, so let me label up the different portions here. So this is our NSH2 domain in blue here, bound to our phosphotyrosine. So this is a phosphotyrosine here on the cytoplasmic side of our epidermal growth factor receptor. Okay, here is our N-terminal SH2 domain, Sarc homology 2 domain, the one that's slightly closer to the N-terminal than the C-terminal SH2 domain. Okay, here is our split plextrin homology domain. Now, We then have an SH3 domain, which I did previously show here, but I've had to move that because it was in the way of where I wanted to put the NSH2 domain. So here we'll then have our SH3 domain. Okay, so I'll colour that in orange. And then finally, in between the SH3 domain and then the NSH2 domain, we have the CSH2 domain here. Okay, so this portion in blue, and that's still bound over the catalytic core and is therefore stopping the enzyme from functioning. So just to finish up the labelling here, here is the plextrin homology domain that was split into these two halves. This is the CSH2 domain here, the C-terminal SH2 domain, because it's slightly closer to the carboxylic acid terminus than the NSH2 domain. Okay, now to complete this up, let's put the portion after the Y box over here, which remember contains that C2 domain and then the carboxylic acid terminal here, and then the portion that was prior to the X box here, which remember contained these 4 EF hand domains, 1, 2, the third one here, and then the fourth one here. And then after those 4 EF hand domains, you then had a plextrin homology domain, and then the amino terminus here. Okay, right, so now let's just colour everything in and get it all looking nice. So here is our plextrin homology domain in turquoise here. Okay, so I'll colour this in turquoise. Okay, so this is our pH domain, which wasn't a split one, remember. Okay, then we have these 4 EF hand domains in purple here. 1, 2, 3, 4. And then we've also got that C2 domain up here, which I'll colour in green. Okay, so what then has now happened is we have recruited our phospholipase C gamma enzyme to the underside of the phospholipid bilayer by binding this NSH2 domain to a phosphotyrosine residue on the cytoplasmic tail of our receptor tyrosine kinase. Okay, but we have not yet activated our enzyme. Our enzyme is not yet activated because this catalytic domain, which is made up of this Tim-like barrel domain here, still has the CSH2 sticking in it, and therefore we can't possibly get a PIP2 molecule in here to actually catalyze the reaction. So the enzyme is still inactive. Now what's going to happen is one of these tyrosine kinase domains is going to phosphorylate that SH2 domain. Okay, so it's going to phosphorylate a tyrosine within that SH2 domain, and when it phosphorylates a tyrosine within that SH2 domain, it causes a change in conformation, and that CSH2 domain completely lifts out of the catalytic core. And then what can happen is this can now bind to a PIP2 molecule in the inner leaflet of the phospholipid bilayer and break it down into diacylglycerol and IP3. So basically, one of the tyrosine kinase domains is going to phosphorylate the C-terminal SH2 domain, and that's what's going to lift it out of the catalytic core, and then you've got the activation of the enzyme. So there's 2 stages in the activation. First, it needs to come and bind up here to localize it in the correct place. Not only to localize it in the correct place so that it is then in contact with the PIP2 molecules in the inner leaflet of the phospholipid bilayer, but also to localize it in the correct place so that the tyrosine kinase domain, which is active within the dimerized epidermal growth factor receptors, can now phosphorylate the CSH2 domain, okay, to cause it to lift out of the catalytic core and expose that catalytic core. So that then is how receptor tyrosine kinase enzymes, which are an example of, for which our example is the epidermal growth factor receptor, are capable of recruiting and activating phospholipase C enzymes of the gamma form. Okay, these are now going to break down PIP2 into diacylglycerol and IP3, and IP3 will then go and release calcium from the ER. So you get the same signal being generated here as you could from a G protein coupled receptor that's GQ coupled, okay, but it's a completely different family of receptors, and it's working through this different family of phospholipase C enzymes. Okay, G protein coupled receptors work through phospholipase C beta enzymes. Receptor tyrosine kinases work through phospholipase C gamma enzymes.